Hi folks, welcome to another captivating interview on Spark Igniting Minds. Today we have the pleasure of introducing Manjunath, an avid amateur astronomer and former software professional. Driven by a quest to find answers to some of life's most profound existential questions, Manjunath's passion for science and astronomy is both inspiring and humbling. With a solid academic background in astronomy and astrophysics from the Birla Institute of Fundamental Research and additional courses from Coursera, Manjunath has dedicated himself to exploring the mysteries of the universe. His dissertation in astrobiology, focusing on the possibility of extraterrestrial life and methods to detect it on exoplanets, highlights his deep interest in understanding the cosmos. So, let us welcome Manjunath to Spark Igniting Minds. Namaskara, Manjunath. It's a great pleasure to have you on Spark Igniting Minds. My warm and hearty welcome to you.
Thank you.
To this platform. And you have been an avid astronomer and also a software professional, and you have got a great curiosity to know more about life and universe that actually impresses us all, and we are more excited to talk about astronomy, the sun, the star, galaxies, and all those.
Absolutely.
And so let us deep dive into.
Sure.
We would like to explore your insights and experiences.
Absolutely.
Welcome, Manjunath, to Spark Igniting Minds. And so my first question to you is, like you have been into corporate or as a software engineer for so many years, and what sparked your interest to get into astronomy, and why did you choose this as a career?
Okay. I have been a software professional. That's what I did for a living. At the same time, I always had a sort of curiosity towards astronomy and astrophysics. But I mean, I had more curiosity for science in general and specifically astrophysics, astronomy. This is something that has been there. This is not new. And in 2017, I quit my job. And I was wondering what to do. Just about the same time, I think I bought my telescope with the purpose of spending more time watching the celestial bodies. And somewhere in between, we had been to a site in New Zealand where they had, an observatory, University of Canterbury, in a place called Lake Taupo. So they have an observatory there, and the man there showed me some of the celestial bodies, sunspots, some stars, and that made me that drove me to have a telescope of my own. So after coming back from that vacation, about 15 days of vacation in New Zealand, and I went about getting my telescope, and around just at that time I quit my job.
And you also did some course in Birla.
Yes, that was after quitting my job. I was looking to do something to enhance my knowledge. So I came across this 100-hour course conducted by Birla Institute of Fundamental Research. The classes were conducted over the weekend, mostly Saturday afternoon, rigorous, 3 to 4 hours sometime, and the staff was excellent. Some of them were from Indian Institute of Science, some of them were from Indian Institute of Astrophysics, ISRO, Bangalore University, all accomplished people in their own fields. And I got a thorough knowledge, sort of introductory knowledge to astrophysics and astronomy, various disciplines of astrophysics and astronomy, and also astrobiology, cosmology. And
so all these are very, very interesting. Astronomy, astrophysics, they're all excellent topics which I think we have, most of us, our common people, may not know more about all this. So what is astronomy, astrophysics, astrobiology, and cosmology? and why should common people get interested?
Okay, let's take one step at a time. I'll give a one-line definition of what those fields are. Astronomy is basically study of celestial bodies, their characteristics, their behavior, and it is an observational science. Okay, all you need is look up at the sky and look at these celestial bodies and know about them. Astrophysics is applying physics and chemistry to analyze the behavior of celestial bodies. You apply the principles of physics and chemistry to analyze the celestial bodies.
Maybe you may have to know the composition of a celestial body,
what is a star made out of? What is the molecular construct of that star and things like that. That is astrophysics. Cosmology is basically study of origin of the universe itself, like Big Bang and what has happened after Big Bang. It is basically the evolution of the universe since Big Bang. That's what is cosmology is about. It is also a discipline which is considered under astronomy and astrophysics. Okay, and astrobiology is a fairly new field. It is the study of possibility of extraterrestrial life, either on exoplanets or even within our own solar system on some of the moons of the other planets.
Okay, even on the moons there are
yes, there are some signs. Yeah, there are the recent explorations that have been conducted by NASA have seen some sort of environment which probably can support life on some of the moons of Saturn. Io, for example, Europa, for example, there is a possibility of life, could be. I mean, so that is also one of the. So basically, astrobiology is about extraterrestrial life and how do you detect if there is extraterrestrial life, either on exoplanets or on some of the moons of our own planets. How do you detect them? So that's what is astrobiology is about. So those are
and cosmology is about the birth of the
the evolution of universe since the Big Bang. So Big Bang has happened.
What is this Big Bang theory? Some maybe everybody knows about it, but still from an astronomer's.
Okay, so Big Bang was a sort of theory somewhere in 1920s or 30s. I forget the name of the astronomer who proposed it. I think he was also a priest, a holy priest in Roman Catholic order. He is the one who actually proposed that Big Bang is what how it would have all started. Okay,
how the universe started.
Yes, how the whole universe started. So then the solid proof for that was found in 1965 when two scientists by the name Arnaud Panzias and Robert Wilson. They were working in Bell Laboratories. So they found out accidentally, they were not really looking for it. They found what is called CMB, microwave radiation, background microwave radiation. Okay, so that is what was the solid proof for the Big Bang to have happened.
And it's still expanding, I think, no?
The universe is still expanding. So the way they say that it is expanding is that there is something called red shift. If you observe a distant galaxy, it appears as if it has been red shifted. So that is a definition which says that the galaxy is moving further away from us. If it was say blue shifted, then it is moving towards us. Red shift means it is moving away from us. Like
galaxy, Milky Way.
No.
All the complete universe.
All the galaxies are moving
the galaxies
apart. Like they are moving away from each other. The whole universe is expanding.
What do we see in the sky exactly?
Okay, a good layman's.
What is the layman's description of this?
Okay.
Yeah.
So let's start at the very beginning. When you look up in the sky, you see as if the celestial bodies are rising in the east, okay, and they go up in the sky and they seem to set in the west, right? And the reason,
like our star, the sun.
Yeah, all of them rise in the east and go up in the sky reach a certain height and then set in the west. Okay. So the reason for that is the earth itself is spinning on its axis, and it is spinning from west to east, right? Yes, and that is the reason why you see the celestial bodies are rising in the east and setting in the west. Okay. Now the stars also basically they rise in the east and set in the west. Similarly, the moon and the sun and everything. So, but there is a difference in the way the stars move and the planets move from east to west. For example, if you look at you go to an open field. Okay, let's assume that you are in a place where there are no mountains, no buildings, nothing, and then you face yourself to the east, and let's assume it is a summer day, right? The sun appears to rise not exactly in the due east, but slightly towards the north. Okay, and if now you turn around to your west and see where it sets. Okay, now if you turn and look at the west, so it appears as if the sun is not going to set. This is the summer time. Yeah,
Slightly towards the south.
Yeah, towards the north. Towards the north, because this is the summer time. Yes. Right. Similarly, if you look at the easterly direction when the sun is rising, if it is a winter time, the sun doesn't rise exactly in the due east, it is slightly to the south. Only on 2 days in a year, March 21st or 22nd, that it exactly rises in the east. Yes, that is called the equinox. Right, that is the equinox when it exactly rises in the east, and similarly it sets exactly in the due west. Right, so which means to say sun's position in the sky depends on what time of the year it is.
Okay.
Right,
is it the sun is a static thing? Is it not? So it's at one place. Okay. It's at one place.
Okay, so now
I don't
know. Okay, so all this is happening because the earth is spinning.
And the earth is spinning. Right? Yes. So it's not the sun.
Okay, so we now described how the sun moves across the sky throughout the year. Okay. Right. So if it is summertime, it rises more towards the north, not exactly due east, and then sets again same way. It sets slightly towards the north, and if it is winter, it is the south. Right, that's fine, but this doesn't happen with the stars. Stars rise and set at the same place, whether it is summer or whether it is winter. Right, and that, so when initially people looked at the way the celestial bodies were moving, they thought we are the center of the universe. I mean, everything seems to rotate, orbit around us. Right, and we don't blame people who assumed that. Right, it gives you an impression as if that is the case, but if you look at the way sun moves, as I said, sun doesn't stick to the same line of setting and rising and setting every time. It depends on the time of the year. And similarly, if you look at the planets, okay, some of the planets they also take the same way in the summertime, just like where the sun rises, that is where most of the planets rise and set. All that is fine, but some of the planets exhibit a very strange behavior. Okay, for example, let's assume that the earth stops spinning on its axis. It's night time, the earth has stopped spinning. So when it stops spinning, because it has completely stopped spinning, the stars become stationary. Right? Yeah, stars, if the earth doesn't spin, the stars will be stationary, right? Whereas the planets are not stationary.
Yeah. Planets are always moving.
Yeah, because
stars are stationary, planets are moving.
Yeah. So what happens is, normally, let's assume that the earth has stopped spinning, the stars are all stationary. Okay. In the normal circumstances, in such a situation, the planets move from west to east. Right? The planets, yeah, no, so the rising in the east and setting in the west is only because of earth spinning. Now we have assumed the earth is not spinning. So because of that, stars are stationary, whereas the planet, they appear to move from west to east. right, basically in the other direction. But it so happens some of these planets, they change their direction. It's called retrograde movement. Okay, so normally they should move from west to east, but sometimes they change the direction and then go back again to the original direction. So all this was contradicting the assumption that we are at the center and everything is going around us.
We are not universe-centric.
Correct.
Yeah.
But people assume
Initially
that
people
we are at the center,
yes,
and everything moves around us. But the behavior of the sun, behavior of the planets, was an indication that we are not at the center. So what the astronomers did, even from the Greek time, they worked out a model which will fit the description of what we see. Okay, various mathematical models, that would explain why do planets move retrograde and then go back again. So, but none of the mathematical models that they came out with satisfied the observation. What they saw did not agree with the mathematical, whatever they tried they couldn't explain. Finally, the only solution that was possible was if Earth was going around the sun along with the rest of the planets, and what happens is and there is a theory, okay, the inner planets move faster than the outer planets, right? For example, Earth rotates around the sun faster than Jupiter or Mars, okay, but faster than Earth is Mercury and Venus, which are the inner planet, right? Now just imagine, like if Earth is moving around and the Mars is also moving around, you can imagine at some time what happens is when the Earth overtakes the Mars, right, it appears as if the Mars is moving backwards because we overtook. That is what is retrograde movement, and this can only be explained if the planets are going around the sun, not if we are at the center of the universe and then everything is going. And that was the basis for coming to the heliocentric principle or heliocentricity of the whole solar system. So we are not at the center, sun is at the center, and all the planets are going around the sun, and some of the planets, when they pass each other, a retrograde motion is possible. It appears as if the planets are changing their direction and then going back in the same direction.
It is because only of the speed of the planets. The inner
fundamental principle, the fundamental law, in fact it's a law, is that the inner planets move faster. And this holds good not just for our solar system, it holds good for even say the Milky Way. So Milky Way is a huge galaxy, right? The objects which are central to the Milky Way galaxy move faster, whereas objects which are in the outer edge of the Milky Way galaxy, they move slower. Their velocity is less. They're basically, so that is the principle on which the heliocentricity was finally agreed upon. Though it doesn't look like that. It looks as if we are at the center, but that's
it's always we feel that we are at the center. That is not the truth.
That is not, yeah.
Other than these planets and stars, we also see some of the other celestial objects also in the sky. Like we may see asteroids, meteors, then comets, and all those. So when we gaze at the sky, what all do we see, and how to really see the sky?
Okay, so for the celestial objects, there are two parameters that define where to locate them. One is declination, other one is right ascension. I don't want to go into the details of it because it becomes mathematical and all that. But these two are enough to locate an object in the sky. If you go look up on many of the websites where the location in terms of the declination and the right ascensions are published, so there are telescopes which are called motorized telescopes. They are attached to a computer, and then you can enter into the computer what is the object that you want to see and what is the declination and right ascension of the object. Then the telescope is automatically focused on that object. Okay, so one thing that you have to remember is the declination and right ascensions are the coordinates of the objects that you want to find in the sky. For stars, the declinations and right ascensions don't change, whereas for sun it continuously changes. And the reason for that is the earth is spinning on its axis, and the axis on which it spins is not perpendicular to the axis on which it goes around the sun. It is at an angle of 23.5 degrees, right? So earth is like this, okay, this is the axis of the earth, and the axis in which it goes around the sun is like this. So because of which we see the seasons, because of which we see in the summertime sun rises more towards the north, not exactly due east.
There is a variation in the day and night also. I think days will be longer, nights will be, that is what we had studied in geography.
The seasons are basically
Seasons are also that.
And
only during the equinox, I think, days and nights are.
Yes, exactly. Yeah. Another question that many people ask me is that, so we know how the solar eclipse happens, right? The solar eclipse happens on a new moon day when the moon comes in between the sun and the earth, right? Because so a shadow is cast on the sun.
So shadow is cast on the sun.
It's cast on the sun, and then you don't get
and
to
then
see
you
the sun.
don't
Right.
get to see
But
the sun.
why doesn't it happen on every new moon day? I mean, right? Why it should logically it should happen, but the reason why it doesn't happen is the moon's the plane in which the moon rotates or goes around the earth is not exactly aligned with the plane in which earth goes around the sun. There is a 5-degree difference, right? There is a 5-degree difference between the plane in
Plane of the earth and the plane of the
no, hold on for a second. The plane in which the moon goes around the earth, that is one plane, and there is another plane which is the one that earth goes around the sun. So both are not aligned. There is a 5 degrees difference. So only on 2 days in a year these two planes meet at a point, and that is the reason why full solar eclipse can happen only 2 days in a year, right? It doesn't happen on every new moon day.
And that is a very spectacular thing on the sky, solar
Absolutely.
eclipse or lunar eclipse. Does it have any reason or a history behind or something?
It is just an astronomical phenomenon. It obeys the light. The light doesn't reach us. That's it. I mean, the photons don't reach us. That's why the photons emitted by the sun don't reach us, because it is blocked by the moon.
It's
So
blocked
that's
by
it.
the moon.
That's
That is the solar eclipse.
Yeah.
When you come to lunar eclipse,
The lunar eclipse happens on a full moon day only, and that is when the earth is in between the moon and the sun. So the earth casts a shadow on the moon, and that is why you don't, again, because of the alignment of the planes in which the two go around. It doesn't happen on every new moon day or every full moon day, sorry. The lunar eclipse happen only on the full moon day and not on every full moon day, because of the 5-degree difference between the plane in which the moon goes around the earth and earth goes around the sun. There is a 5-degree difference.
sir, universe is so vast, and where are we on the universe?
Oh,
What
that
is
is-
our location?
that is a very
and
interesting
also,
question.
what is the size of the
Okay,
universe?
that's a very good question. Okay, according to the studies that have been conducted, the observable universe, which means the universe from where the sun, the light reaches us, the radiation reaches us, that is about 92 billion light years. Okay, or 42 of how much ever it is, half of 92, that 46 or whatever, 46 light years, billion light years in all directions. The universe is 46 billion light years in all directions.
From our Earth.
From us, basically.
Earth, huh.
The universe is spread 42 light years.
Million light
sorry,
years.
billion, not million, billion light years
Billion
away
light years.
from us.
Okay.
Right? So okay, now
It's
that
huge,
is
we can't
that
even-
is only the observable universe, and beyond that there could be more, but the light doesn't reach us. That's why we don't know, right? Okay, now according to one reliable study that has been done, the observable universe is interspersed with 400, get this number, 400 billion galaxies.
Oh my
Right?
goodness. In that, Milky Way is one of the galaxies.
We are not done yet. We are not done yet. Okay. And another study done by European Space Agency, it has estimated that the Milky Way galaxy is home to 100 billion stars. Now, if you take that as an average and multiply that by the number of galaxies that we just talked about, which is 400 billion galaxies, now you can do the math. 10 to the power of 22 stars. Can you believe that? I don't know what is it called. Heptalion, sectalion, I don't know what billion it is called. So 10 to the power of 22 possible stars are there only in the observable universe. Beyond that,
we never know because light doesn't reach.
Okay. Now, according to one estimate, I'm just extrapolating from there, trying to get what is the possibility of life on some of these, stars. Okay, some of these stars, according to one estimate, now we have come to what is the number? 10 to the power of 22 stars in the observable universe, right?
What is one star means? 10 to the power of 22 stars, you said.
Yeah,
usually we say light years.
No, this is number of stars. We are counting number of stars. Yeah, we are not calculating the distance. It is just sun is one. The nearest star is Alpha Centauri, which is 4 light years away, and that is not one star. It's a binary star. Okay, so if you go on counting all the stars, just in the Milky Way galaxy, there are about 100,000 stars. Sorry, 100 billion stars. Okay, now you do the math. 1 billion is 10 to the power of 9. So 10 to the power of 9 stars in the Milky Way galaxy times 400 times 10 to the power of 9 number of galaxies in the universe, and it comes to about 10 to the power of 22 stars in the observable universe. Okay, according to one estimate, about 5% of these stars are similar to that of our sun. And amongst those 5% of the total, about 20% of them have what is called a habitable zone. Okay, what is an habitable zone? It's a zone around the star where the temperatures are moderate. There are possible life sustaining
elements in it.
Environment.
Maybe a climate, and also
Yeah.
you can think of the geological aspects,
Water.
water.
Go one step at a time. So that is the kind of estimate people are now making. So the possibility of finding, first of all, possibility of life there is. Because sheer number is humongous. Right, the number of sun-like stars, it will come to about 10 to the power of 17 or 18, the sun-like stars.
Out of them, how many habitable?
Yeah, that is the question. That is the question. That is what we are trying to do now. We are trying to look at exoplanets. An exoplanet is a planet that is orbiting some other star, not sun, right? So we are looking at exoplanets only within the Milky Way galaxy.
Sir, let us talk about the stars. Like what are stars made up of? What is the composition of the stars, and what are the attributes? And also, what are black holes?
So first question is, what are stars? Stars are nothing but burning mass of gas and some interstellar. So stars are born in stellar nurseries. There are some areas in the universe where there is lot of debris, lot of dust, cloud that is probably left over from Big Bang, but unlikely from Big Bang, because Big Bang is 13.8 billion years ago. But now what you see is lot of dust and gas from a leftover star, a star which has died. Stars have life cycles, by the way. So when the star ends its life in say an explosion or whatever, it leaves behind a lot of dust particles, gas, dust, clouds of. So the matter just swirls around and acquires
and then they
mass.
form another star.
Yeah, so swirls around, acquires some mass, and when you talk about mass, there is gravitational attraction. So the matter, combines, not exactly combines, but comes physically close, and then it forms a swirling mass, right? Okay, that is how the stars are born. Okay, so
And they also keep combining something. I heard hydrogen and helium keep.
okay, hold on for a second. I'll come to that. Okay, so the stars are basically formed in such stellar nurseries by acquiring matter, clouds of dust particles and all that, and then it takes a long time, maybe millions of years. So finally, a star comes into existence. Star now has acquired some mass. So what drives the star is the thermonuclear fusion that goes on inside the core of the star, right? So when you talk about a star, there are two forces that come into picture. One is the great attractive force, the gravitational force, which pulls everything towards the center of the star, right? No, that is the gravitational force. Okay, the second force is the result of thermonuclear fusion that pulls apart everything.
Okay.
So one is pulling everything inside, other one is pulling apart everything. So if there is a balance in these two, then the star is stable, like our sun. Our sun is currently experiencing exactly what I described. So there is gravitational attraction which is pulling everything towards the center, and there is a force because of thermonuclear explosion, because of the fusion that is happening, that is pulling everything apart. So these two forces are in perfect balance, and that is why sun is stable, right? What happens is, so the thermonuclear fusion that is happening on sun is basically fusing hydrogen atoms into helium. So hydrogen atom is basically one electron and one proton, there is no neutron, right? So four atoms of hydrogen combine together to form helium, and there is a difference in mass between 4 atoms of hydrogen and 1 atom of helium. The difference in mass is completely converted into energy using E is equal to mc square, the famous Einstein's, so then that is the reason why there is so much of light that is coming, radiation, I mean electromagnetic radiation that is coming out of the sun, and also at the same time there is an attractive force which is pulling everything towards the center. That is why sun is stable, otherwise it would have exploded.
And so have they predicted even the sun has to die one day because death of the star?
So what happens is, such stars which are in perfect balance are called, they are in main sequence, they are main sequence stars.
They don't have death.
No, they do, but it takes a long time. A star can stay in main sequence, which means in perfect balance between the two forces that I just talked about. It can sustain itself for about 10 billion years. Okay, a typical star, there are exceptions. I'll come to that point. What is an exception? Why does a star, what is the difference between a big star and a small star and all? I'll come to that point.
Some are explodable stars.
Hold on for a second. Okay. So right now we are talking about a typical star like that of sun, which burns hydrogen and forms helium, thereby a lot of energy is released, and it is a stable star. And sun is, they have calculated that sun is going to remain this stable state for another 6 to 7 billion years. Okay, no problem. We are going to be
we are going to be there.
Okay.
Earth is
now what happens? Some stars, they run out of hydrogen. Okay, so there is no hydrogen left for the fusion to happen. So then what happens is, such stars, they go out of the main sequence. They start combining helium itself, okay, and form some other elements of the periodic table, and they move out of the main sequence, and then they become, say, red giants or super red giants. Okay, sun is also supposed to go after about 6 billion years. It might become a super giant, a red giant, which means it will bloat. It will bloat so big that it will engulf even, say, Mars within that. It will become so big. Okay, so that is the future of sun, future of any star. Now, okay, now everything so I was talking about the formation of the star, right? So the behavior of the star depends on how much mass it acquires at the beginning when the star is formed. Okay, if it acquires too much mass, much bigger than sun, such stars become unstable. They live shorter actually. They don't live for 10 billion years and all that. They live shorter. They have a very violent, very explosive death, right? And they shine very bright. When they are alive, they shine very bright. So that's what happens to stars which acquire a huge mass compared to suns at the beginning. Then on the other hand, the stars which acquire very little mass compared to sun, they live a boring life. The comparison given usually is the big stars which acquire a lot of mass, they are compared to rock stars. They have a very colorful
life and a short life.
right? Very colorful, very extravagant, energetic, and they die a very explosive death. Whereas the stars which acquire very less mass, they live for a very long time, but they live a boring life. They end up being what are called brown dwarfs. Okay, they run out of energy, they become dead stars like hard rock, mass of things.
And the brightness also decreases.
The brightness also decreases. So in between stars are more interesting to us. Sun-like stars.
Sun is a star which is an in between.
Right now it is in the main sequence, right? So you were talking about black holes. So there are some stars which let's assume they have much more mass than sun at the beginning. Okay, such stars, after they move out of the main sequence, they become unstable because they have more mass than what can keep it in a stable state. So there is more gravitational force attracting everything towards the center. They become so strong gravitationally, they don't even let the light go out. So those are the ones which end up being black holes. So our Indian scientist Subramaniam Chandrasekhar, he came out with a mathematical formula to calculate what should be the mass of what is called a white dwarf. Okay, there is something called a white dwarf, which most stars or many stars end up becoming white dwarfs. Okay, not the very small ones which end up being brown dwarfs, not the very big ones which end up being supergiants. So in between stars, there are some stars, they may, because of the excessive mass, they end up being white dwarfs, and Subramaniam Chandrasekhar calculated what is the stability criteria for white dwarfs. Okay, he said, mathematically he calculated if the white dwarf has a mass which is 1.4 times that of the sun, it has a possibility of becoming a black hole or a neutron star.
So it doesn't emit any light. The whole light is inside. That is why they are called black holes.
Let's go back to what Chandrasekhar said, Subramaniam Chandrasekhar, for which he got Nobel Prize in 1983, though he did it in 1932. When he was a 21 or 22-year-old young man, he was on his way to UK to study astrophysics. The story goes that he wrote this up while he was traveling by ship. Okay, so more importantly, so he calculated the limit for a white dwarf. If it exceeds that limit is 1.4 times the mass of the sun. If it exceeds that limit, either it will become a black hole or a neutron star. Okay, black hole it will become if no, they are different, slightly different. I don't want to go into details of it. It will be like too much of this one. So if the mass is too big, bigger than 1.4, but say maybe around 10 or 12 times, then it becomes a black hole. If it is slightly bigger, then it becomes a neutron star. Okay, neutron star, very basic thing without going into details. Neutron star is where the whole mass is consisting of only neutrons, no electrons, no protons. It's all just neutrons. So that is a neutron star. Okay, so now what we have talked about is the life cycle of stars, right? So
how does a star take its birth?
Yeah.
And then how does it even explode?
Okay.
Which are the stars?
Yeah, okay. There's another point that I would like to highlight. So I said stars have a life cycle, right? They are born, they exist for a while, they die, okay, and then they are reborn. So now the theory is our solar system consisting of sun and the planets is either a second or a third generation star, which means previously there was a star which died and again another star was formed and
that died. And
why do they say that? Why do they say that? The reason why they say that is, suppose if it is a first generation star which is burning only helium, which is only burning hydrogen and forming helium, will end up having no heavy metals. Like say, so heavy metals are formed like environment of high pressure and temperature. Some of the elements, some of the higher elements, higher than helium, they combine, they fuse, nuclear fusion, and then heavy elements like iron and those are formed. And so when a solar system is built out of such debris, right, then you will have those elements even in the planets that are formed. So planets are formed when
that's how we have all the minerals,
exactly,
iron,
but
and all
we
this.
also have even heavier elements like uranium and all that. So that is the reason why they say our solar system is not at least second or third generation solar system. So yeah, so that is called the metallicity of the solar system. Like say if the heavy metals are found, then its metallicity is higher. If it is a first generation star, you will not find
Maybe
anything.
all these iron and all heavy metals, maybe in other planets also, other than Earth.
Could be,
because
could be.
could
I
be,
mean,
no?
could be. I mean, like the appearance of Mars is reddish, right? It could be iron oxide. I mean, it's not that it could be. Probably it is. I mean, yeah. So iron oxide is what.
Iron oxide. That's why it appears
Yeah,
red.
yeah, rust.
Is it? And
Rust,
I have
right?
heard that the blue star, something which is blue in color, will emit more light than the.
First of
is
all,
more
planets
temperature. They have some temperature also.
No, planets don't. So you are talking about star. Blue stars are, the temperature of the blue star is very high compared to
The
a
red
star.
star. That's what
Yeah,
I was trying to tell.
yeah.
So there is a temperature difference
right,
also.
right.
That's why it appears blue.
Right.
If
Blue
it is
stars
more,
are more, they are emitting more energy. The surface temperature is higher for a blue star than a red star. For example, for sun, the surface temperature is 5,600 degrees centigrade.
so it's
or
a
Kelvin,
red
yeah.
star, is it?
No,
Our
ours is a
sun
yellow
a
star, right?
Yellow star.
Yeah.
Okay,
yeah.
okay.
So yeah, so red supergiant. For example, there is a star called Betelgeuse. You can see that in the Orion constellation. So that is a supergiant, red in color. It's basically a red colored star. Okay,
And also, how are stars classified, sir? Like classification of stars are there? Like something A, B.
Yeah, so based on the surface temperature, I don't want to go into details. There is an alphabetic classification. I also don't remember exactly right now, but there is a classification, and that is based on surface temperature.
Surface temperature.
Yeah. And there are a couple of other factors. Surface temperature is one of the factors that is used for classification of the stars.